is in charge of the Cosimulation framework. He's one of the developers of this Cosimulation framework that we will get more in detail in a while. My name is Ernesto Pérez. I'm a professor of Universidad Nacional de Colombia. I'm one of the researchers. I'm the leader of the project P9 of Energetica 2030. That is a program, a research program with 10 projects. I am leading one of them. So I will start with why we are doing this and why we need this new framework for control systems and the power systems. And the idea is that traditionally we used to have large generation plants. These generation plants are centralized and are big, and they have more of the generation that we need in the demand. And we have small plants, and they are less than 10% in general. Mainly, we have hydraulic, thermal, and there is a predicted production. And nowadays, they are changing because the new technology, we have new ways to generate electricity. So eolic and solar generation has become really popular because of the cost. It reduced the cost, so now it's really competitive with the other technologies. And this gives us new ways to generate. We are in a transition of decarbonization of our planet. So it gets new dynamics in the system. So we have high variability in generation production. Now the distributed generation is becoming larger and larger. So we have a lot of the distributed resources in the power system. So it makes new dynamics that we have to take care. There is a really high forecast uncertainty. So it's really difficult to forecast long term the generation that we will have. So these challenges makes us to change a lot. So we are focusing Colombia right now, and Colombia is a power system that has a matrix, energy matrix, really hydraulic. Also, more than 60% is hydraulic, and then it's thermal. But now we're becoming really fast to get new type of generation, especially solar and eolic. And there are some projects, and the idea is to include the projects in 2, 3, or 4 or 5 years. We'll have up to 7,000 megawatts. So it's more like 30% of our current production in current capacity. And all the technology is going to be placed mainly in the north part of Colombia. And it takes a new ways to analyze what the power system is right now. So there are some other countries in Europe and United States that has faced this challenge before. However, we are trying to just be in the same way, and we are developing with these partners a lot of the new technology that we need to control this type of systems. Another thing that we are facing right now is that we have a lot of outer generation. So in Colombia, it's increasing the outer generation, and around the world, especially in countries like United States and California, there's mandatory also new houses to have auto generation. So it's becoming more and more popular, and it makes us a new challenge in the operation of the power system. So the other ways that the transportation is the electrification of the transportation is becoming more popular. For example, Colombia is one of the countries who has become more electric in cars. In Latin America is a country that is increasing more the the production of sorry, there is someone with the microphone. Okay. So the sellings in Colombia is getting bigger. We are facing new challenge in the infrastructure and also in the control of this technology, because it will be really hard to control the church of the control and try to understand what is happening with the demand. So we have more active demand in our power system and is facing new challenge in the control room. So what we're facing right now, we are having a new actor that is called prosumer, that is someone that can produce energy but also consume energy, and it's really distributed in the system. So we have a lot of interconnections that they are interacting more actively than before. We can have new actors like microgrid, a simple microgrid that has several prosumers here, but also something that we are calling virtual plant. It's commonly that you aggregate several microgrids and then you try to dispatch these microgrids centralized, or probably they can be separated also. And then we have our traditional power system. So they are facing new things in this part. So something that, for example, I want to show you an example of what is happening that we have to take care when we are forecasting our demand and our generation production. For example, in 2014, our independent system operator predict a forecast the demand of the day, of this day. It was a particular day, but the demand just have a different behavior that day. And it was really interesting because this behavior is due to social activities. And this social activity in Colombia particularly was because we were in the World Cup and we were facing one of the match, Colombia versus Uruguay, and the demand just go down up to 20%. So these type of things make us think that we have to take care about different conditions, not only the electric variables, but also other conditions. For example, we have to take more concern about the traffic, because now we are having a lot of demand that is becoming from the electric cars. We need to face about the new social conditions and the disease. So like today we have COVID and it faces us a new things to forecast the demand. So it's something that we have to take care. So we have to combine all these things to make a control system more reliable and efficient. So what is happening right now in our power system is that our power system is something that is becoming more nervous. So our balance between demand and the generation is changing really fast. So we are facing that it has some movements here really fast that we have to take care, and our control system and our supervision system must be prepared for these conditions. We have to continuously see what we can do. So in this case, we start with our power systems. Since it's a critical one, we need that they are more reliability, strength, redundancy, response and restoration, and all these we can group in a term called resilience. So our system more has to have more this feature, and that's why we are trying to study this part. So this project, Energetica, has one of these projects that is called Power System Supervision, Operation, Protection, considering the high penetration of renewable energies. So we want to develop some technology that make us be prepared when we have this challenge to come abroad that is coming really fast. So every day we are trying to become more active in this thing. This particular project are involved Universidad Nacional with our real-time lab, XM, that is the independent system operator, with his lab of innovation and co-simulation called Linux. There is also Internexa, this is a communication company, and it has also a cloud service that we are trying to use, and Universidad Pontificia Bolivariana with his power system group. This project that is within Energetica is also supported by some international allies. Some of them, if you have been in the previous webinars, some of them have been participating here, especially really tied with the University of Aachen and also Institute of Jülich. But we have also interaction with the University of Catholic University of Leuven, the TU Delft, and also the Technical University of Eindhoven. We have in this project more or less 30 to 40 researchers that are working in this part. And we have divided this in several objectives. I'm gonna show you a little bit. We have some, sorry, because this is in Spanish, but we have some objective that is related with the forecast of generation and demand for real-time applications. We have the unit commitment of real-time dispatch of our plants. Some objectives related with the supervision, how we can supervise and control this system with these new dynamics that we have, and some protection schemes that need. All these objectives are within a framework of a co-simulation lab and a strategy just to make a new ways to supervise the power systems. For this reason, we need especially an architecture of communication, also to analyze the protocol that we need to make this interoperability and reliability in the communication way. So in this way, we can move to the concept that we are developing, especially in this co-simulation lab. And I will give the word to Juan Pablo to continue with this type of presentation. Thank
you. Well, thank you very much. Maybe, Professor, can you make me presenter so I can share my screen? One second. Set this up. So I guess you can see now on the screen. That's correct?
Yes, Juan Pablo, you can.
Yes. All right. That's perfect. Well, so as for to say, my name is Juan Pablo Noreña, and I want to talk about how co-simulation environments, and more specifically, our co-simulation environment here in Energetica Intetreinta is helping us to create a roadmap towards modern power system control centers. So let's say that modern energy systems are expected to be multimodal, as Professor Ernesto said, and incorporate a diversified matrix of sources to achieve the maximum usage of every form of green energy available. That's the main goal. It's a vision that the distributed nature of these new resources and the high penetration of inverter-based generation require a more fast, reactive control and protection of our systems. Other important aspects are the inclusion of storage capacity as utility scale batteries and vehicle-to-grid approaches that introduce very interesting dynamics to the system. The demand response, the participation of load in energy management through microgrids, virtual power plants, and other kinds of aggregation of these prosumers. Also, we have an increasing market competition-driving behavior in our system that introduce other dynamics that have involved very human dynamics around markets in energy systems. So because of these characteristics, modern energy systems can be classified as complex. And naturally, concerns about emerging behaviors might be arise. So the monitoring and control of modern energy systems is expected to be characterized by a distribution of these functionalities, these dysfunctions that must ensure the correct orchestration of the system. So to ensure this optimal coordination, we will need to use a significant use of communication media, computational capacity. This is a vision because, or due to the increasing number of controllable devices that we will have in our system. So the intricate interactions between these domains makes necessary to enlarge the observability of the system. Now we're not talking just about a power system. We're now talking about a system of systems, as we can see here. And by means of the advanced monitoring strategies, we can enlarge the observability of this system of systems. For example, the wide area monitoring strategies and reducing the time steps between measurements of power systems can be useful for enlarge the observability of power systems. But for the other domains, we also need to implement IoT techniques or kind of techniques that allow us to enlarge the observability of this landscape system of systems. In this context, the Smart Grid Architecture Model, or SGAM, is a significant contribution since it provides a descriptive representation of the relationship between the functionalities of subsystems in smart grids and provides as well a structured basis for the design, development, and validation of solutions. Here in the figure, we have the SGAM overview that Matthias also presented in this paper the past year, where they propose the whole elements that integrate the smart grid architecture model, the domains, the zones, the interoperability dimension among these domains and zones, the layers that we have, the communication layer, the information layer, the function layer, and the business layer. This is very important and is like a point to start for us. So a modern control system, a modern control center, is software-based. Is based on software modules that must ensure the interoperability, the security, confiability, cybersecurity of the system of systems, its functionalities, integration, and performance assessment. For the sake of the presentation, we will call power apps to these software modules that must take this role to ensure an optimal coordination of the system. These power apps may run on-premise that they not normally done in the past, but also it's the moment to start adopting some new solution architectures, such as solutions in the cloud or even in the edge. This interoperability is super interesting. As you see here, we have to ensure the interoperability of several domains, since the markets domain, the ICT domain, the bulk power system domain, and these new participants as microgrids and virtual power plants. For example, in Colombia, we're very interested in this topic. For example, the group SIGRE C216 proposed that we have to face some of these challenges soon to ensure optimal transition to the future power systems. So here we have the the most common applications or power-ups that we have in a modern control system. The blue ones might be the most popular, as you can easily recognize some of them. Here we have the state estimator, the reserve monitoring, load forecasting, etc. Even some of them might be now called as legacy tools, since there are new tools that might be more advanced functionalities for enhanced dynamic observability, assessment, and decision support tools. The yellow ones are applications that are on the rise, but you can find a lot of them and a lot of approaches around them in the literature. So here we grouped some of these applications into 8 groups. I would like to highlight the energy management system that have several power-ups that must ensure the correct operation of the system in the steady and dynamic states. But also we have some more like modern applications such as digital twinning. Digital twins are software-based abstraction of complex physical systems or objects, which are connected via communication link to the real object or system through a continuous data flow from the real world. The digital twin makes possible to reflect the physical conditions in real time by linking the physical and digital domain, the physical and digital world, and provide dense analytics for the system it mirrors. It's a very interesting application that is going to be in the core of the modern power system control centers. Then, as Professor Ernesto said, ICT, information communication technology, have a very important role now. Accurate and responsive power systems must incorporate high demands of ICT. For real-time monitoring and control applications will depend on high end-to-end performance and the scalability of this technology to guarantee the correct working of the applications. So robust middleware services that are able to operate with variable resources and multiple source sensor data will be indispensable for advanced power-ups. Then the increasing complexity of power systems lead to the development of new approaches in power system communications. Legacy but still widely used SCADA protocols such as IC104 or DMP3 for TCP/IP communications between the control center and the substations or other distributed elements are supplemented by new data modeling approaches. I would like to name some of them. Maybe most of you will recognize the IC331-118 protocol, the synchrophasor protocol, that enables the growing number of applications in one pack. This wide area monitoring, protection, and control applications considering PMU technology. The IC61-850 standard, the substation automation standard that defines a modern communication protocol for power systems, which is based on advanced and expandable data models and include the definition of appropriate data exchange services. This protocol provides abstract models that can be mapped to various communication protocols. This is very important because we will need to ensure the interoperability among several participants, and the protocols will be in the center of this. Also, other non-traditional internet protocols, I may say in this context, because in IoT applications, they have been widely used in the few past years, but I think that, we think that they fit very well for messaging among distributed real-time applications. One of them is the XMPP protocol, the Extensible Messaging and Presence Protocol. And the upcoming version of IC61-850A will provide a mapping to this protocol. And these protocols working together will enable the integration of decentralized energy resources, loads into smart grid, into smart energy grids, and into smart energy markets. Also, we have the messaging queue telemetry protocol that works in this publisher-subscriber pattern or producer-consumer pattern that provide a lightweight to messaging among the applications that we have. It's very popular in IoT and it's highly scalable. Finally, the HTTP protocol is extremely popular. It's maybe the most common protocol that we use in our regular lives. So it's important to consider it and its functions in new power system control centers. Well, also the Common Information Model standard takes a significant role in the power system industry for data exchange. It's applicable at transmission and distribution level and using a hierarchical approach which is close to database structure. It's really important because this will enable us to make our scenarios or data exchange portable and standard among all the participants in the operation of the system. The CMOL is extended regularly to adapt to new factors such as the market models, the communication elements, graphic models, and new grid components. And the harmonization approach between this SIM standard and the IEC 61850 protocol is also an advantage. Well, that's the overview. What now? So during the past few years, planning, designing, and implementing these applications, these power apps, and other type of applications in modern power systems have experimented a shift paradigm. How is that? In the sense of how these approaches are tested and validated to ensure a harmonized transition. So that's the question. How we can ensure a harmonized transition to accomplish this integration and this transition to these modern power systems. So we have been following the work that some European projects have done in the recent few years. For example, Reserve and Eurogrid, both of them have proposed that we have to holistically address this process of validation rather than using the traditional component level approach. This is becoming more relevant since the developers or the researchers of these applications needs to have a comprehensive vision of their applications before they get implemented in the real power system or this system of systems. So in Energetica, we are trying to follow this path that these two projects have set. And they both had proposed some methods. Reserve had proposed the interoperability testing approach, and Eurogrid had proposed the holistic description method that, in the words of the authors, facilitates the conception, the construction, and reproduction of intricate experimental designs in domains of cyber-physical energy systems. So here we have the abstraction layers of the HTD method. We can see that the HTD method in the interoperability of testing is at the same level of the energy domain smart grid architecture model. So that means that they are pretty related. So if we want to test new applications that must be applicable and ensure the interoperability with the SGAN, we should use the HTD guidelines, and that's what we are trying to do here in Energetica and more specifically in the Cosimulation laboratory. So if some of you had the opportunity to attend the presentation of Professor Antonio Monti that is today with us also as attendee, he has presented the architecture of the real-time super lab that virtually interconnects multiple labs, multiple infrastructures, and not only that, multiple researchers to work together for enable the performance of large-scale scenarios to perform holistic validations of applications, physical elements through power hardware in the loop, as we can see here in this graph. Maybe I should zoom in to make it more visible for you. As you see here, they interconnect several remote labs using this framework called BLS Node that it's pretty important for us in Energetica because it's a tool that we also use. We also are trying to implement to have our very own co-simulation laboratory, also with distributed resources, with distributed infrastructure, geographically distributed. So in this work, they virtually interconnect several laboratories among the world, some of them in the United States, some of them in Germany, and other in Italy. And well, that was a pretty interesting, this is a pretty interesting paper that we follow as inspiration for what we will show in the end of this presentation. Also, if you have the opportunity to attend the presentation of Professor Andrea Benigni, he talked about how real-time simulation enable or benefits the testing of modern energy systems. Here is a architecture that they propose in the paper. They show in the paper how they close a big loop that have a power in the loop elements, real-time simulation elements, physical IDs, communication, ICT elements, protection elements, etc. They also have a software-based control room that includes an SCADA and phaser data concentrator. But very interesting is that they include a cloud architecture or a cloud solution that runs several power apps that close this loop among these applications. So as Professor Ernesto said, here in Energetica, we are developing also several applications. We have several teammates working in dispatch, protection schemes, control algorithms, forecast algorithms, microgrids. Real microgrids are being employed in the project. So the Cosimulation Laboratory want to ensure this environment to the scientific ecosystem to make them available to do these holistic validations of their applications. So for that, we had to develop our very own high-level architecture of a co-simulation laboratory. Here, this is our architecture. Sorry, I need to zoom in this part. We are virtually interconnecting 3 laboratories for that. Let's say that 2 of them are located in the same university and will be coupled by a fiber dedicated channel, so they may seem as one laboratory. But we have 3 different locations. One of them is the Universidad Nacional de Colombia, with the Laboratorio de Gestión de Sistemas de Tiempo Real y el Laboratorio IS 60850. We have the Laboratorio Linux in XM, the Colombian National System Operator, and we have the last one in the Universidad Pontificia Bolivariana at the Renewable Energy Laboratory. So what's the idea? What's the idea of this? This virtual intercommunication is possible thanks to the fiber channel, the dedicated fiber channel that Internexa has provided us, that interconnects the 3 laboratories. And what we are trying to do is, as I said, using tools such as BLS Node, virtually interconnect our simulators or real-time simulators that we have. Also implement some non-commercial real-time simulators, these open source simulators like the PCIN, and also incorporate other tools that we envision that could be pretty useful in order to develop this environment, this very complete environment for testing these applications. The open historian too, as a PDC, as have SCADA functions, and so on. And that's it. Well, we also are trying to as we say, start testing these digital twinning applications. So the idea is that we want to interact with the real world, with the real measurements of the real world. So we are having a connection with the ONCE network here in Colombia, As Mauricio Hernandez from XM said in a previous webinar, XM have the ISACnet that have this WAMS network with several PMUs around the country, most of them located in the north of the country because that is where the distributed generation is going to be located. So we want to use that data to start implementing these digital twin applications. Also, as Ernesto said, we have really big interests in going and test cloud solutions for power systems. So Internexa is also very essential in this part because he's trying to provide us a cluster of a private cloud where we are trying to adopt these good practices that we have seen in other industries, such as Kubernetes cluster and containerization of applications to make them scalable and easy to deploy. And we want to test the applications that our teammates in Energetica are developing, as the dispatch, the intra-RDS dispatch, the very novel automatic generation control algorithms, and so on. So in order to make this a cyber-physical environment, we are also trying to make the power domain and the ICT domain pretty close and trying to represent a reality that have these both domains pretty close. So we are doing some emulation of the network and traffic of communications using Linux NetM and QDisk to like make more close to reality this environment. As we said, also it's not or strong now, but we are trying to also test power in the loop elements. We are starting with this HVDC bank of tests in UPV, in the UP, sorry, but we are now thinking to acquire some other elements to let us to perform bigger and more complex power in the loop, power in the loop scenarios of applications. Also, it's very important that we're very interested in the integration of virtual power plants and aggregator EMS that hierarchical control several microgrids. In Energetica, we have 5 microgrids that are being deployed around the country. Some of them here in Medellin, some of them in Sucre, and so on. And the idea is make this also a close interaction with these microgrids, because they're like a place to experiment with these virtual power plants and the interaction between the virtual power plants and the orchestrator of the system of systems, this advanced power control center. So that's it. That's the architecture that we are proposing. We're trying to work pretty close with the developers of some of these applications. For example, as I said, the team of Professor Antonio Monti, Stephen Bohel, and Marcus Mirtz are the developers of these applications that we also are trying to prove them in the cloud. We are interested in have real-time simulation in the cloud. We also have in the past work close with the developers of Open Historian, Richie Carroll, and so on. So that's the main goal for us, having a really interesting environment that not only for the scientific ecosystem of Energetica. The idea is in the future to make this environment available to be a service for the sector in Colombia, and if possible, sometime make the connection with the global RT lab among this interesting and very huge infrastructure, and be also part of Cosimulation as service for the world, for the huge and large testing that these European projects or these United States projects are working on. So that's it. That's the what I wanted to present, how the Cosimulation environment will enable this reality that we are dreaming on, that we want to make possible for Colombia particularly, but we're learning a lot from what other countries and what other people have done around the world. So thanks to Energetica 2030, the sponsor, the Ministry of Science in Colombia. Here we leave the contact of Professor Ernesto Pérez and me, and the teams that are participating in this development. So thank you very much.
Thank you, Juan Pablo. So right now we want to make this more participate. So I would like to ask so all the participants. So you can do a participation by several means. One is the chat. So the chat is open, so you can make some questions or comments if you like. The other is raising your hand. So if you see the participant window, there is next to your name, there is like a hand. You can just click there and we can see it and give you the opportunity to talk, or just open the microphone and try to say something. Is any question or comment? If you don't feel comfortable with English, you can ask it in Spanish, and we just translate it and put it in English. So feel free to interact with us with all the. Let's see. We have. Yeah. Meanwhile, there are some questions. Marcus Mills. Marcus said, recently I learned that the group behind IC 6150 seems to work on mapping to JSON. And so it's very interesting. Maybe this could be interesting to study as well in this project. Yes, JSON is something that is becoming really popular in all the internet framework. So it's really popular. So it would be really interesting. I don't know, Juan Pablo, if we have something in mind about this.
Yeah. As we said, we are testing these non-conventional protocols or ways to perform, or to messaging among the applications. XMPP, for example, and QTT are pretty popular, but also HTTP communication through JSON are increasingly popular. So that's true, Marcus. The idea is to start taking into account these all mappings that are appearing and try to test them and see how it works, how it goes, because maybe we're too attached to the past protocols such as IC 104, and for what we want, we need to start leaving that behind. So that's true.
Okay, there is another question or comment from Franco Anibal Castillo. How is the interoperability with other countries like Europe and North America? Professor Monti
if Professor Antonio is here and he may be able to bring his mic, it will be awesome, because he's the lead of this project that have interconnect Europe and North America. So that, yeah.
Yes, I'm still here. Sorry, I didn't really understand the detailed question related to the interaction.
Yeah, the question is related. How is the interoperability within other countries, so like in Europe and North America?
Oh, if you look about it, well, that was one of the reasons to start this experiment, this what we call a super lab idea. And the idea was that basically there is clear signal that there will be in the future some sort of global grid. At least the Chinese are planning to build it. And that triggered the question, are we interoperable or not? So the question was never considered before because they were totally independent, thousands of miles separate systems. But if somebody will, as it looks like, build basically a ring at high voltage DC close to the North Pole, then we will start exchanging energy between America and Europe. And this is a totally different scenario. So the Super Lab started actually because the Department of Energy in US started talking to the European Commission in Europe to start wondering what kind of question will we have in interoperability in the future. So short answer is early stage. There is nothing concrete. And our lab was a way to study in the future how this interoperability could be arranged.
Okay, thank you. There's something here also. I will say within the country, it is really hard to make interoperability. So, for example, the lab of IEC 61850, we have tested a lot of different vendors of manufacturers of protection, and despite they state that they work with IEC 61850, there is really hard sometimes just to make this interoperability in real. So there are a lot of things just facing that we have to face in this new digitalization of substation and all the work, that I think there are a lot of things to learn, and probably these type of projects let us just go in this direction. So it's really important. I have another question from Andres Duque. He's asking, how do you synchronize all the measurement in a real-time simulation? I don't know if Pablo, you want to answer that?
Yeah. We are using GPS synchronized clocks among the laboratories. Each one has his very own GPS in the facilities, and we are experimenting. Well, we are using these protocols such as network time protocol, NTP or PDP, to ensure the synchronization among the laboratories, because this is one of the most important things when you are trying to do real-time simulation or have these real-time co-simulation environments. So we use this physical GPS that ensure the time synchronization among the distributed participants of the experiments.
Yeah. Good morning. One question: what is the capacity of the current real-time simulation environment that it is available within XM laboratory? I mean, how many buses can new technologies such as modular multi-level converters be simulated?
Well, in XM in Linux, they have this Opal RT simulator that has 8 cores, and they have now, up to now, simulated the entire Colombian power systems. I don't know if Professor Ernesto can remind me the number of nodes that the Colombian power system have, but it was done in phasor domain. So, Professor?
Yeah, it's more than 700 nodes, and it's also simulating the interconnection with Ecuador. But I think you were also talking about to testing converters. So
Yeah.
right now we don't have all this capacity. We are just trying to improve and upgrade part of the laboratories to make a power hill in the loop, so we can include some power there. But also because we interconnected several labs, we have also in the university, we have an Opal RT equipment also. And we are using this open source simulation that Professor Monti has been developing that is called DPSIM, and it will increase our capacity of simulation. So we are able, we haven't tested the limits, but we think we will have enough capacity just to simulate several countries in Latin America. So it will be, I don't know if Brazil is huge, but we are trying just to implement this, and probably we can interconnect with other simulation labs that we can do that. So it's the way that we are doing right now.
Well, also I would like to add that also the simulator have capabilities to use HyperSim. HyperSim, it's able to simulate these fast and complex dynamics that you can find in this type of converters. We're now starting to test some models that we are interested on. But if you want, you can write me to this email, and I can give you further information of the capacities.
Okay, thank you.
You're welcome.
Maybe specifically on the MMC, if somebody's interested, I know that both Opal and RTDS offer a special extension based on FPGA to perform an extremely detailed simulation in real time of MMC converters. I think both of them are offering on FPGA.
Just to interrupt, this is Mauricio Sanchez here from XM. We haven't done yet, or we haven't put yet all the interest in MMC simulation, because currently we're just working with a project that is going to interconnect all the wind capacity that is going to be in the north of Colombia in the coming years, and some of the project that is going to interconnect that generation with the central system. We're thinking to use an HVDC. Some of the uses of that HVDC will be in MMC, using MMC. So far we haven't got the interest yet to simulate that, but in the coming years, hopefully we will have to do it in using our FPGAs. So it will be much of our interest to know if you have done it in your lab. Of anyone there has achieved that goal to simulate that technology using FPGAs.
Thank you, Mauricio. Yes, we are just trying to cooperate with other labs so we can take that. As a research, we're also trying to improve this part. We don't have yet, but I think next year we will get into more this EMT simulation. There is another question related more about Energetica. Is Energetica 2030 open for people looking to start in research? How get more information on the various groups and subjects? Yes, Energetica is a huge program, like 10. We have 10 projects, or 11 actually. Also, I think here this is our scientific director, Jairo Espinosa. I don't know if you want to say some comments, Jairo, or I answer.
Oh yes, the idea.
Yeah, loud and clear.
Yes.
Okay. No, I think the remarks are coming to the point where basically what we are doing is to enhance a strategy that is a complete the complete connection of different systems. So currently we are working not only with the simulations of electric systems, but also with interactions with other kind of systems, including, as Ernesto mentioned at the beginning, mobility is one probably one big demander that will need some interaction. But also the idea is to get up to the point of making simulations of policies. Therefore, the complete view is really going for the full standards of interconnection among the different environments and different areas of this developing of these so-called virtual worlds or digital twins. That's it. Thank you.
Okay, thank you, Jairo. Just to answer Juan Pablo, and also there is another comment from Andes University. So the idea to connect with the project, as I mentioned, is a huge project. We have several, like 10 projects in different areas of energy. You can connect through the leader of each project. You can actually, we are in maintenance of the web page, but you can send me an email. So my EPSG, so I can connect you with other projects and show you. The connection for institutions, just to make this alliance that we have called Energetica, we are open to this. So you can also write me an email. I also lead another part of the project that is called Fortalecimiento Institucional. So it's trying to just to improve all the institutions that are marked here. So we are really open just to new partners in this project. So we can get in touch, and probably we can see something that we can do to improve our cooperation and to enlarge our partners in this project.
Ernesto.
Yes.
Yes, I was thinking that maybe we can take advantage of the Andes University in the interest to join the project. Maybe we can start some cooperation with them in the topic of power electronics. I don't know how is the Andes expertise on that topic, but we have to put, in my opinion, more effort and more resources to investigate power electronics and take advantage of the tools that we already have in our labs.
Yes, Mauricio, thank you. So there is another email that you can contact. It's not here, but it's for Jairo Espinosa, that you can connect this. And there is another that is more institutional. I will write down here in the chat. So you can, through any means, you can contact us. We are really active in the social media. So we are also getting some institution trying to contact us to just improve all this strategy. I didn't mention that this strategy is funded by the Ministry of Science in Colombia, but also by Ministry of Education and the Commerce Ministry here. So we are looking forward to have a sustainability of this ecosystem that we are developing. There is another ecosystem that is called Seneca, and that we work also together in some parts. That at the end we need a sustainability and research, or large research in energy. So all the partners that can connect with us, it will be really interesting in this project. So we are really welcome. So I will expect for your email. Okay. I don't know if there is another comment or question. Okay, I will say that this webinar will be also be online on YouTube in a couple of weeks. We are just putting some material in the YouTube channel at Energetica, and in our Facebook and all these social networks that we are connected to. So thank you very much. I don't know if there is another comment or some question that anyone wants to participate.
Hi, Ernesto. Hello,
Yes.
hello for everyone. I have a little question about the interoperability. All the equipment must be outdated or only the digital networks?
Let me just give me a second. And yes, I think it's my point of view. It's really hard just to make a huge transformation of all the infrastructure that we have just to make it interoperable. We just need, we have some experience just to start with one of digital substation and start improving and upgrading the other ones. So for example, Colombia, they are developing this type of studies, and they are trying also with the Linux lab, trying just to get more interoperable and just to include this. But it will take several years to get really interoperable all the systems. So I think this is my point of view on the knowledge that I have of some of the experiments that they have developed. So I think just to change all the infrastructure to make it interoperable, it will take a long time. For example, the United States are really conservative. They still have a lot of electromechanical protections because they're still in use and they operate well. They have some limitation, but they're starting just for new things changing. It's something that I noticed when I was there. I don't know if there is someone who works in this that wants to add something. Okay. Okay, if there is no more comments or questions, I will thank you, everybody. Thanks all the people who worked in this project to make this possible. There are a lot of effort in this project. There are a lot of cooperation, and it's been really pressure just to work in this type of project, user project. I would like to thank everybody. We can see in the next webinar, we are having this webinar every 2 weeks with new subjects. One of the subjects will be SIM, and we'll take, I think it's in November, but we'll have talk about models and protection in the next webinar. So we will send you some information about that. Thank you very much, and goodbye.
Thank you all.
Goodbye.